Hey everyone, and welcome to This Explainer. We're jumping right into a classic today. It's one of those deceptively tricky problems that pops up in coding interviews literally all over the world, sorting an array filled with nothing but zeros, ones, and twos. Now, it sounds kind of easy at first glance, right? But finding the absolute best way to solve it, well, that's actually an incredibly clever puzzle.
Let's set the scene. Imagine you're sitting right in the hot seat of a technical interview. The interviewer slides this problem across the desk. You smile, you're ready to tackle it, and then they drop the ultimate constraint. Hey, can you sort this in just one pass without using any extra memory? That right there is the real puzzle. We're not just sorting numbers anymore. We're trying to do it with absolute ruthless efficiency.
Okay, so how do we tackle this? Let's start exactly where most of us naturally would, the brute force approach. The most straightforward answer you could give your interviewer is to just rely on a standard, trusted algorithm. Something like merge sort. It's reliable, it divides the array, merges it back together, and eventually everything is perfectly in order.
Now, merge sort will absolutely get the job done, no doubt about it, but it comes with a hidden cost. It runs in O of n log n time. Plus, it requires a whole separate temporary array just to do the merging. So you're looking at a space complexity of O of n.
And right on cue, the interviewer shakes their head. Nope, too slow, too much space, I need you to optimize it. They're definitely not going to be happy with that logarithmic time, and they absolutely hate that you're eating up extra memory. This rejection is actually great, though, because it forces us to look closely at the data we actually have. We don't have just random numbers. We strictly have zeros, ones, and twos. So we pivot. We present our better solution, the counting approach. Since we know exactly what's sitting in that array, why not just tally them up? We iterate through the array once, keeping 3 simple variables to count exactly how many zeros, ones, and twos we're dealing with. Then we just iterate through the array a second time and manually overwrite the values. If we counted 5 zeros, we literally just write 5 zeros at the front. Then we overwrite the ones and finish off with the twos. Easy.
Look at the progress we've made here. We've completely eliminated the need for extra space. By just overwriting the existing array, our space complexity drops to a beautiful O of 1. And our time complexity? It improves to O of 2n, simply because we had to loop through the array twice, once to count, and once to overwrite. But remember, we're in the hot seat. The interviewer leans in and says, you're taking 2 iterations. I don't need 2 iterations. Give me 1. Okay, things just got serious. They want us to eliminate that second pass completely, but we still have to keep that perfect O of 1 space complexity. How on earth do we do that? Well, this is where we get to dramatically introduce the hero of today's explainer, the Dutch national flag algorithm. This is it, the optimal, truly best solution. It's a seriously clever technique that uses 3 separate pointers moving simultaneously to categorize and sort every single element in just one single iteration. There's a fantastic quote from our source material that I absolutely love. It says, "No one is talking about the intuition. I'll be focusing on the thought process." And honestly, that's exactly our mission today. We are not just going to memorize steps or stare blankly at a block of code. We're going to build a visual intuition so deep that you'll be able to confidently explain the why behind every single move to your interviewer. To build this intuition, let's grab our tools. The whole algorithm revolves around 3 simple pointers: low, mid, and high. Think of these 3 little arrows as our heavy lifters. They're going to traverse the array and perfectly swap numbers right into their correct places. Now, here is the absolutely crucial part. The whole algorithm hinges on maintaining 4 distinct hypothetical zones based on exactly where our pointers are. Think of it like a map. From index 0 up to low -1, that's our guaranteed safe zone for zeros. From low to mid -1, that's the safe zone for ones. Way over on the right, from high +1 to the end of the array, is our safe zone for twos. And right there in the middle, sitting between the mid and high pointers, that is the messy, completely unsorted territory. The visual metaphor we're going for here is actually super intuitive. Our entire goal is to shrink that unsorted middle section until it completely vanishes. When we start, mid is at the very beginning, high is at the very end. So literally the entire array is that unsorted unknown section. We're going to attack this unknown section one element at a time. Let's break down the 3 rules of attack. Okay, rule 1. This happens when our active searcher, the mid pointer, bumps into a 0. What do? Simple. We swap the element at low with the element at mid. Then we just bump both the low pointer and the mid pointer forward by 1 step. But wait, Why do we do that? Well, think back to our map. The zeros belong all the way on the extreme left. By swapping with the low pointer, we're securely locking that zero right into its permanent home, growing our sorted block of zeros. And since we just secured it, we advance our midpointer to go check out the next unknown element. We also have to advance our low pointer because our block of ones just got shifted over to the right. Make sense?
All right, moving on to rule 2. What if our mid pointer encounters a 1? Oh, you're going to love this. It's the easiest step of the whole algorithm. We literally do nothing to the array itself. Nope, no swapping at all. We just move the mid pointer forward by one single step.
Again, focusing on the intuition. Why do we do nothing? Because the ones naturally belong right in the middle of our Dutch national flag. If our mid-pointer lands on a 1, it's already exactly where it's supposed to be, nested safely right after the block of zeros. There's no need to swap it anywhere. We just acknowledge, yep, you're safe, and advance our search pointer to the very next unknown element.
Finally, we have rule 3. This is what happens if our mid-pointer hits a 2. In this scenario, we swap the element at mid with the element way over at our high pointer, but pay very close attention here. We only move the high pointer backward. We do not move the mid-pointer forward. Why is that? Well, 2s belong on the extreme right? So we grab that 2 and we literally shove it all the way to the back. This locks it into the sorted right-hand section, which effectively shrinks our unsorted section from the back end. But why skip moving the mid-pointer? Because the element we just swapped in from the high position used to be part of the unsorted section. It could be a 0, it could be a 1, or it could even be another 2. We basically have to analyze this newly swapped element on our very next step before we can move on. So, picture this happening. With every single step we take, whether we're applying rule 1, 2, or 3, we are actively eating away at that shrinking unsorted block in the middle. Either the mid-pointer pushes forward or the high pointer pulls backward. Every single operation means exactly one less unknown element in our array.
And that brings us right to the finish line. How do we actually know when we're done? Well, the loop completely breaks the exact moment the mid-pointer crosses the high pointer. Why? Because if mid is suddenly greater than high, it means our unsorted section has completely disappeared. There's literally nothing left to check. The zeros are neatly on the left, the ones are sitting perfectly in the middle, and the 2s are just chilling on the right.
Which perfectly sets up the victorious punchline of this entire explainer. Big O of n. In every single step of this algorithm, either the mid-pointer stepped right or the high pointer stepped left. That means we evaluated each and every element in the array exactly one time. No going backward, no double counting, just one beautifully clean sweep.
When we put it all side by side, the results are undeniable. Look, the counting approach was definitely good. It used O of 1 space, but it still required 2 full iterations, so it clocked in at O of 2n time. But the Dutch national flag algorithm, it grabs that exact same perfect O of 1 space, but pulls off the entire sort in strictly O of n time using just one single iteration. We have officially and fully satisfied the interviewer's ultimate constraint.
We've moved way past just rote memorization today. You now possess the visual intuition for exactly how those 3-pointers operate in the wild. So as we wrap up this explainer, I want to leave you with a question to chew on. Now that you have this deep intuition, how are you going to apply this brilliant shrinking the unknown mindset to your very next algorithmic challenge? The next time you're facing a brutal constraint in an interview, just remember those pointers, picture the safe zones, and keep shrinking the unknown. Thanks so much for tuning in and keep on learning.